Hi stats students. So welcome to lesson 7 in unit 1. Today we're going to be talking about model distributions and density curves. So those might sound pretty scary. I will hopefully make them less scary rather than more scary, but this is a kind of a very basic concept that again might seem a little difficult at first. There's going to be a lot of little details and vocab terms and stuff, but again, once you start using these things in problems, it's gonna slowly, actually not even that slowly, but it'll make more sense. So without further ado, let's get to talking about these. So what do I mean by this term model distribution? So again, in math, when we're talking about a model, we are talking about some kind of like known entity that we can easily work with that can stand in for something else. The most common kind of models we talk about, say, are like linear equations. When we use linear equations or like a simple linear function to stand in for some more complex real-world process. Why might we do this? Models are simpler than real-world things, right? Real-world things are messy. Models are not. Models are things that can be like well characterized. We can know things about them. We can calculate things about them. We can create one if we have the right kind of information. Whereas with real-world data, getting real-world data is hard. Like usually that means setting up an experiment and taking measurements. It means like going outside with a, with a clipboard and asking people questions in a survey, right? Real-world data is hard to gather. It is hard to work with. Models, like if we can come up with models that can stand in for our distributions, kind of the way that, say, a linear function can stand in for something. If we can find models that we can use the same ways, models that resemble, like very closely resemble real-world distributions, especially common ones, if it's something that we can represent with a mathematical function, that's great, because then like if we know the right inputs, we can create this distribution. We don't have to go through the process of collecting a ton of data. And another side benefit of this is anything that kind of is generated from a mathematical function, it's very knowable, right? And it is something that is workable by a computer. A computer can then, like if we have the function, then, we give it a little bit of information and a computer can generate this distribution for us. And this is really what we're searching for, right? We are searching for a kind of an easy stand-in that enables us to do a lot more things. So again, we are not trying to replace our data. We still need that data, but what we're saying is once we see the distribution of the data, let's see if there is some simple, well-known thing that is really close to it or close enough to it that we can kind of make that substitution. There are a lot of types of model distributions that statisticians use. So this is like a map of sort of the most common ones. We are not going to be going through all of them. At most, we are going to discuss 4 of these in this course. Actually, no, sorry, 5. We're going to discuss 5 of these distributions in this class. Really, we're going to heavily focus more on 2 or 3. The nice thing is they all have their own specific types of situations they are useful for. They all have these sort of unique specific shapes. So when we make a histogram of our data, we can look at that shape and say, okay, this kind of looks like this other type of distribution, so why don't we try to use that as our model? Or, right, based on the type of situation we're discussing, a certain model might make more sense. This will especially become clear to us when we start talking about these binomial distributions. That's going to be in a few chapters. And so there, right, it's more you look at this situation, you say, ah, this is a binomial situation, and that's when you know to use this distribution. Other times, like I said, you mostly just like look at your data and say, well, that's kind of close to this other shape, so let me try using this as my model and, you know, see how well it kind of recreates my original data. So we're going to start off our discussions of model distributions with the sort of the two most simple ones, okay? And then as we go further, we'll start adding in some useful ones that are like useful for specific situations. These two are very simple and very kind of general. So the absolute, complete, 100% most simple distribution shape is a uniform distribution. A uniform distribution is flat. There is no peak to it. All the values in your data set are very evenly, equally distributed across the entire range, right? They are not, as we have seen in most of the distributions we have worked with, that's not usually the case. Usually data is mostly concentrated at the center and it kind of gets more spread, like less and less and less as you get further away. Right, so we end up with like a peak in the middle and kind of very low tails on the outside where there's not much. A uniform distribution is different, right? That is flat, like there are no low tails or high peaks, it's just flat. Everything's the same. So the most common uniform distribution that most of us encounter are dice rolls. If I have a 6-sided die, the probability of any of these numbers, of getting any of these numbers is exactly the same, right? 1 6 1 6 1 6 1 6 1 6. So this is something we can model, like when you actually do it in real life, like if you are bored, like if we go into a second lockdown now and you just get really bored and you want to shoot a die all day, and like log what results you get, sure, there's gonna be a little bit of wiggle in there. I ran a simulation with sort of 500 different random dice rolls, and you know, the 5s and the 6s and the 4s kind of came out a little bit more often than the others, and we'll expect that with real world data, but you know, by and large this is very, very flat. So we could model this with a uniform distribution. Again, uniform distributions are really simple to work with because it's just a constant value. There's not really much of a function. It's basically piecewise, right? Like you have some height in the middle, like from one value to another value, from start to stop. But then before the start and after the stop, it's just 0. Nothing will pop up there. I can't shoot a 6-sided die and get a 7. That's not going to happen. I can't shoot it and get a 0 or a -1, right? There, I only can get 1 through 6. Anything else, there is 0 probability that I'm ever going to get a dice roll like that. So in my distribution, I'm not going to get anything there, right? It's kind of 0, goes up, and then comes back down. The next simplest type is, it's hard to call this one like simple necessarily, but in comparison to the other types of distributions we use, it is mathematically, if you were to see the formula, it is a little ugly. There's a lot of stuff going on. There's like exponents and letters and all kinds of weird things, but in the grand scheme of things, it is a fairly easy function to work with, right? It is called the normal distribution. That tends to be the term that's used by statisticians and mathematicians. Well, actually, I don't know about mathematicians, but statisticians and data scientists definitely like to call this the normal distribution. In the engineering world, I was an electrical engineer as an undergrad. We always called these Gaussian distributions. Named after the German mathematician Carl Friedrich Gauss. Very cool guy. Well, not necessarily a cool guy, but a great mathematician. And so here, right, this is very much this kind of classic bell-shaped symmetric distribution, right? This is just the classic random bell curve. for a lot of reasons. It actually does pop up quite a lot, which is part of what makes it very useful. Anytime you're looking at a completely random variable, let's say height. Well, even height is not completely random. But say like in physics, if we're talking about, the amount of energy that different electrons have or something, they will tend to have this very like nice, simple, basic, normal curve. Say like the intensity of a laser, the further you go out from its center is gonna follow exactly this kind of a pattern. So it pops up in any kind of fully random process, which means it pops up a lot in science. And it also pops up anytime that we are, say, like we're trying to make an estimate of a measurement. And so we take a bunch of samples and we measure out those samples and we look at that distribution, say like a distribution of averages. Those will come out as normal distributions. And that is something we will be doing a lot in this class, starting in, I forget what it is in the new sequencing, whether it's like unit 5 or unit 6. But when we get to things about sampling distributions, we're going to be seeing normal curves all over the place. So they're really common in, say, like physical sciences when you're taking measurements. They are really common whenever you're taking, again, like anytime you're doing sort of repeated measurements and like working with samples. So that means that for like scientists and statisticians and stuff, everyone is going to be using this at some point in some problems. So they're very common, or they represent like very common kind of distributions. And like I said, they're relatively very easy to work with. Especially for computers, right? At this point, any calculator, any computer program is going to be able to work with a normal distribution very accurately and quickly. We can generate and what's nice is all you need to make them is a mean and a standard deviation, and that's it. Those are the only two things you need to know to make one. So these are the main two that we're going to work with, especially the normal distribution. But for right now, I'm going to talk a little bit more about the uniform distribution because it'll help us understand the more basic concept of working with a model distribution. Because the way we work with them is not going to be entirely the same as how we work with like real life data, like lists of numbers. These are going to be a little bit different. And let's see how. Actually, before we get to that, let's do some practice. So, in Pear Deck, right, we'll sort of, pause the video now, go ahead and answer this question. I will, sit here patiently. But basically, right, here's two different distributions, two histograms, and we want to think, is there a model that we could use, especially thinking about the uniform and the normal distributions. Could these be useful models for these distributions? You might be sitting here thinking, okay, immediately B is probably very obviously, it looks like a normal curve. It's going to be very nicely represented with one, right? We see the peak and we see the kind of the small tails. And it's nice and symmetric, right? This is going to be really nicely modeled with a normal distribution. For A, this one's a little trickier. We could go a couple of different ways for this. Immediately me, when I look at it, it looks flat to me. Especially because it kind of just like it drops off very quickly. From what we can see here, right? It drops off immediately at 5 and like immediately after 20. So we're gonna end up with, so that makes me think uniform distribution could work really nicely with this, right? Kind of running, let's say if it was like up around 30 or something here, right? It would kind of look something like this. If on the other hand, you were to tell me, Miss A, Are you really going to tell me that looks like just like a nice flat surface? Like, what about these big dips and everything? In this case, I might not argue with you. I might also argue with you about this, because this is always going to be a situation we run into when we're picking models, is that, like I said, sometimes life gives you a really pretty distribution and you just know immediately, okay, this is the normal distribution is going to work and it's going to be great. There are other times that data is noisy and messy, and the way I kind of refer to this is you sort of have to squint, back up, squint your eyes, blur your eyes a little bit, maybe take a shot of vodka or something, just get it real blurry. And you kind of have to just not see that noise. How much noise, when we can just call it noise versus no, this is actually a different looking pattern, is in a major way a judgment call. So in this case, I would respect a judgment call going either way, either using a uniform distribution or saying, no, I would not be comfortable using either of those models, either of these two as a model. But again, models are super useful. We want to use a model, right? We don't want to get to a situation where we say, I don't have a model for this data. Because models are going to be the thing we use to make predictions, to generalize to other similar phenomenon. All of the really interesting things that you can do with data is really going to come from the models rather than the data itself. The data is a starting point for us to create a model. Which might kind of sound funny, but that's generally how math works. We don't want real world things because the real world is messy. We in math, in stats, and in all other math, right, when we're dealing with real world problems, we are trying to strip away that layer of reality. We are trying to find some simple idealized pattern underneath. And those simple idealized patterns, that's just another word for model. So modeling is essentially what we're always doing with math. In stats, we're just a little more upfront about it, I think. And I think we're a little more humble about how good or not good our models are, right? We always have to recognize our models can fail us, but they're also where all that useful stuff comes from too. So, all right, this is going to be kind of the annoying part. So whenever you're in class, this is maybe the part that we should focus on in our discussions. But I will try to do my best here to go over this in a simple way. So, right, we have histograms to represent real-world data. But when we have these model distributions, they come from mathematical functions. Right, they're going to be these nice, smooth curves, right? We see the same thing here with the uniform, right? A nice, smooth line versus the kind of this broken up bunch of bars. And so where does this come from? What does this mean? So with the histogram, remember, right, the whole idea of a histogram is you are not treating your x-axis, your range of values, you are not treating it as one continuous number line. We are explicitly creating chunks, right? We're saying, okay, we are turning the range from, say, 7 to 8. We are turning that into a bin. Anything between 7 and 8. So like 7.1, 7.4, 7.23692. All of those go inside this bin, right? So we're kind of aggregating things, we're collecting things, and we are splitting up this continuous number line into a finite, a countable number of what we would call discrete things. And each of those things, I'm just going to call them here chunks, just to kind of make the language a little bit friendlier, right? We can still call them bins, we can call them categories, we can call them, really, if you want to be sort of professional about it, we would call them intervals, right? Intervals on the range. right now, just to be playful, I'm going to call them chunks. But if you want the real vocab, it's interval. So these chunks, each of these chunks can have a relative frequency, right? This is what we've been doing so far in this unit. Right, say like, when we say relative frequency, we mean, say, 20% of the values came within this interval. Were between 7 and 8, and like 15% were between 8 and 9, and 10% were between 9 and 10. Right, so each of those chunks can have a relative frequency, right, because they are containing multiple points of data. And they're representing these kind of very discrete blocks, chunks on the x-axis. So those chunks can have relative frequencies. The problem now with our model distributions is they don't do that. They are not breaking up the number line. These are what we call continuous curves. They don't have breaks in them. They don't go from like this bar to this bar, right? All the values go one into the next. So really you can kind of think of it two ways. Either you can think that these things don't have any chunks, right? They are not splitting up the number line, or you can think of it kind of in a different way where there are infinitely many chunks, right? Every single possible decimal value is kind of like its own chunk on a continuous curve. But either way, it's not like some nice countable number, right? When we're thinking about it, it's either like 0 or infinity. Those are kind of weird numbers. And so they're not going to behave the same way, right? We can't talk about relative frequency with these densities, with these curves, because all we have now are single points, single values. We're not kind of aggregating things together. And each point represents this infinitesimally small little value or small little interval. So like the likelihood of anything showing up really precisely on exactly that decimal value is basically 0. So we can't really directly call this like relative frequency. If we're thinking like what is on the y-axis of this thing, we can't really call that, we can't exactly call that relative frequency. We're going to call it but it does show us something, like the fact that there is a peak, the fact that this is higher in the middle is telling us that that is where our data is more likely to be, right? When we look at this red curve, it follows the same shape. There is some relationship there with the relative frequencies that we see on a histogram. But we're going to use a different term here because, again, relative frequency doesn't quite really describe what's going on. We're going to call this density. And specifically, we would call it like probability density, right? So there is like the probability is, you can think of it almost as being like heavier here in this range versus like towards the tails. So when we think about the y-axis for this normal curve, the y-axis would not be relative frequency, it would be density. So these are going to be related but not identical concepts. So how are they related? Okay, so we can use density to determine a relative frequency, or really what we think of as like, so with relative frequency, right, we are talking about the actual number of times that some data has popped up, that some kind of values have popped up, right? We are literally talking about a frequency of things, frequency of responses relative to some total. With a model, we're not really thinking frequency because we're not really thinking of real world stuff. We're not thinking of actual trials that have actual values. We're talking just a hypothetical shape. So I'm gonna use the terms relative frequency and probability kind of a little interchangeably here. Because the idea is if I have this normal model, I can ask, for instance, here, this is showing time in minutes. And we can ask a question, well, what's the probability if I were to be taking measurements? What's the probability that the time that I get, the time that I measure, is 240 minutes or less? If we actually did this and, say like 500 times, we measure out this time interval, and we take 500 measurements and we make a histogram, we could still ask that question, right? Like, what percentage of the times were 240 minutes or less? In the model, right, it's more predictive. It's not really describing existing data. It's modeling, you say, future data, right? So now we're saying, instead of saying like what percentage of the times were 240 or less, what we're really saying now is, if I do it again, what's the probability that the next one is 240 or less? Or if I keep doing this, what's the probability that any measurement will be 240 or less? So, right, this idea of probability and relative frequency, they're talking about the same thing, but say one is past tense, right? Relative frequency is kind of a past tense measurement, right? It's looking at data that's already been taken. Probability from the models is a future tense kind of thing, right? This is specifically talking about the probability of future results. But they still kind of are talking about the same thing, right? Just different verb tenses here. So the way that, so we call these curves that map out the densities, we call them density curves. And the way we find these probabilities from these density curves is we look at the area under the curve, or the area between the curve and the x-axis. The amount of area that's down there within a certain interval. So say here, right, we're kind of marking off at 240, and we're marking off all of the area under the curve that is below that, to the left of it. And we're saying, okay, what percentage of the total area is contained here? So if we were to look at the area under the entirety density curve, it would be 1. Because that's kind of how we set these up. That's literally how we get the density values. It's so that if you find the whole area under the curve, it will all kind of total up to 1, which 1 as a percentage is 100%. So it makes sense, right? If we take the whole curve and everything under it, we are looking at 100% of the distribution. If we're then just looking at some particular range, now we're talking about some percentage that's less than 100. This looks like ballpark to me. This looks like it's close to, I don't know, close to a third or maybe a fourth of the area. Okay, maybe a fourth, maybe a fifth of the area. I don't know. So let's say like 20% of the area. So that would be the thing, right? If we found the whole area under here and we compare it to this area, this would be like 20% of the whole. So every density function, the area under it is going to be 1, representing 100%. So let's see what this looks like in practice. So here we're gonna skip the normal curve right now. That'll be its own lesson in lesson 8. We're gonna just talk about the uniform distribution now. So, right, we have a random number generator that's coming up with random numbers, including decimals. Oops, sorry, I'm gonna have to edit that. That's supposed to say between 0 and 5. I kind of changed the problem in there. So between 0 and 5. So it could pop up with 1 exactly. It could pop up with like 1.232 or 3.141, any kind of number in that range. And every single number has like essentially an equal probability of popping up, a flat, consistent probability. So remember, the area under this curve has to equal 1. So if the width of the curve is 5, right? It goes from 0 to 5. So the width is 5. If we remember, right, the area of a rectangle is length times width. So if we have that the area is length times width, area is length times width. And so we know now the width, so we know the area is 1 and the width is 5. Then the length has to be, change up my marker here. Right, we have 1 is now the length times 5. So the length must be 1/5 or 0.2. So now, right, we figured out sort of like where the top of this density function needs to be, so that the total area underneath is 1. So the density there is like 0.2. So now we can ask some questions, right? So now we know like sort of how tall this the density curve is, and we know how wide it is and everything. So we can ask, right, what percentage of the generated numbers will be between 2 and 4? Okay, so we want to look now specifically between 2 and 4. So I'm going to try some fancy thing here where I do a little screen sketching. Oops. Did not want that. Okay. Oops. All right. Guess I cannot do that. I will do it on my whiteboard then. Let me figure that out for the next video. So we have essentially this rectangle going from 0 to 5. The height is, right, 0.2. And so now we're asking, right, what percentage of generated numbers, or we're saying basically what is the probability that the next generated number is between 2 and 4. So, right, we see 2, we see 4, and we want to see like what is this area going to be? Okay, what is the area between 2 and 4 in this case? So, well, again, this is a simple area problem. Area is length times width. So in this case, let's say the length is 0.2 and the width is 2, right? 0.2 up and down, 2 side to side. So if we multiply these two, we get 0.4. Or equivalently, 40%. Okay, so the proportion would be 0.4, the percentage is 40%. Number 2, what percentages will be less than 3? So now here, right, we're gonna set it up a little differently. So we're starting at 3 and we're basically shading down to the end. So now we're going from 0 to 3. We can do a similar calculation, right? In this case, we're gonna have 0.2, that height, times 3, which is the width, which gives us 0.6, or 60%. So, next lesson, we're gonna be trying to do similar things for the normal curve. Unfortunately, it's not going to be quite so easy, but this is where our calculators and computers are going to help us out a ton. So thank you guys for listening. Thank you guys for watching. If you have any questions, ask me during class, or if you're not in my class, feel free to ask me in the comments. Hope you have a wonderful time. See you for the next lesson.